Hello, and welcome to the fascinating history of calculus. Just kidding, it's the history of volume, calculus edition. So, remember when volume involved things like 1/2 base times height, or 3/4 pi r cubed, or even something as simple as length times width, and not things like pi times the integral from a to b of our area function? Well, this is how calculus has changed volume. Summations are another evolution of volume. Yeah, these things, no one likes those. No one likes them at all. Summations are basically the ghost or the Benedict Arnold of the calculus world because happy American history moment, everyone feels betrayed by that one kid who prefers summations and makes everyone look bad in front of the teacher because we just don't get it. Kind of like what Benedict Arnold did with England and Washington, the rat. So now the question is, where does volume even come from? Well, it's a 2D image that evolves into a 3D image that evolves into a 4D something tangible, kind of like Pokemon or Digimon. Take this basket, for example. If this system creates a 2D image of half of our basket, then the area of this 2D image, or the integral from a to b of our upper function minus our lower function, would equal the integral from a to b of 18 minus 1/2 x squared, with 0 and 6 being our limits or boundaries, and this integral produces the area between our curves. Short evolution break. Remember when circles went with pi r squared? Well, we're not escaping that because of cross-sectional area, except our radius is now our function, unless it's a washer. Then the inside function creates our second smaller radius. Now volume is going to equal the integral from a to b of pi times our upper function squared minus our lower function squared, unless we're revolving around the y-axis. Then it's our farthest x limit squared minus the inverse of our function squared, and a and b become their y equivalents. So technically, we look at the graph like this when we're revolving around the y-axis. This ends up producing our volume as the integral from the y equivalence of our previous lower boundary to our previous upper boundary of pi times our previously furthest x value squared minus the inverse of our equation squared dy. But since we can't use y, we pretend like it's an x when we plug it into the handy-dandy calculator using Math 9 to solve our integral. Notice how the answer doesn't necessarily change with minor simplifications. Now that we have our answers, we must always round to 3 decimal places. It's basically the plus c of all calculus equations. So where does volume come from? Well, we took a 2D graph, used integrals to find the area of a 3D slice, and combined these ideas to find the volume of a solid represented by this equation here.